Oh yeah, it's L plus 1 and x times j. Okay. Um, even so, wait. This is called upward. Wait, this is called upward recursion because I start from the lower values of, L, and move upwards. The problem is that this method is unstable for smaller x. So even a very small run of errors can become a larger error every time I calculate the next value. Now, as I inc- as it increases, L increases, the error can grow significantly. So even though the recurrence formula is mathematically correct, the numerical method becomes inaccurate. Okay, we can see this one later. Now for my downward Bessel recursion, okay. Now to solve the problem, I also use downward recursion instead of starting at L equals 0. L starts with I start with L equals 50. Okay, I mean wait, I just end this one, but it's okay. I use arbitrary starting values because I will normalize the result later. Then okay, this one my values and my down values is 0 times n and n plus 1 down values n equals to j. Now after wait then I use a for loop, okay, that decreases L from 50, which is my 50th n, so to 1. Okay, I use the same recurrence relation, but now I am moving downward instead of upward. Okay, after reaching L equals 0, I normalize the values using the known value of j. Okay, known value of j, and then of j, which is sine of x. Okay, which is sine of x uh, divided by x. This gives the calculated value correct scale. Now, downward recursion is more stable for this problem because the numerical errors do not grow the same way they do during upward recursion. This method is related to Miller's algorithm. Okay, so as you can see, I have my scale. Okay, uh, I have my scale right here now for L in range n plus 1 down values equals to down values times scale. Then I print 1 equals to 0, down values 0. So as you can see, we can do uh, my down values. Okay, now uh, for my relative error, okay, uh, error and we will be using the relative error and graph. Now, uh, I'll calculate the relative error for both upward and downward. Okay, which is this one, up upward error and down error. I use absolute difference. Okay, uh, difference between the calculated values and the reference values divided by the both. By the absolute value of the reference value. Then I plot there against L. Now, if L is equal to 0, then return okay x, and then if true, if it's equal to 1, then we will return mat that sign mat sign x to the power of 2 mat cosine. Okay, then we will do okay. So basically this is my function for my exact bezel. Now for n in range, okay, 1 until 2l, then my jm, okay, my variables right here, this is 1, then return the j. Now it will put this one my upward error and downward error. Okay, now uh for l in range 25, then my uh exact bezel upward error, then is the band obs, then I'll use absolute value, okay, of the reference value, which is up values, and then my down values. Okay, we use, okay, absolute difference, okay, between the calculated value and the reference value, okay, divided by the absolute okay, values of the reference value. Now, then I plot the error, okay, error against L. Then I use a semi-log scale because the error can change by a very large amount of number. Down the upward recursion should show the error increasing as L, okay, as L becomes larger. The downward recursion should remain much more accurate. Okay, this shows that the downward recursion is much more stable for this problem. Now, uh, let's try to run this one. Okay, okay, uh, my result. Give me this, and then this is my okay Bessel function. Okay, if I don't think you can see the graph, but it's showing on my screen, but it's not being recorded, so I'll just state what's in there. So as I can see, I can see my downward recursion more stable because uh it is 10 to the power of 0. Okay, my downward recursion. But let's see my my result for my first one. Okay, the standard formula, which is x equals this one. And then my reformulated formula is x2 is equal to negative. Then my relative difference. Uh, Now for my part A2, my direct, and then so on and so forth. Okay, and this one is my for my upward recursion. Okay. As you can see, it keeps increasing at first, but then it goes down. Now this is my downward recursion. Now downward recursion is much more stable than my upward recursion. Then my relative errors, as you can see, this one, and then so in conclusion, this activity showed me that numerical errors can happen. Okay, even when the mathematics and formulas are correct. First, in part A, I learned about subtractive cancellation and how reformulating an equation can reduce the loss of precision. In part B, I learned the Taylor series can become inaccurate for large values because of runoff and cancellation. And reducing the input can improve the result. But in part C, I learned that a recurrence relation can be unstable in one condition, in one direction, and stable in another. Okay, uh, which is my downward error was much more stable than my upward. Now, the important thing is that I learned how to do this, even though it's really long. So, I think that's all for today. Thank you.